The new topic is ideal shaft power cycles. In the previous topic, we discussed various types of gas turbines and various types of processes within the gas turbine system. For the analysis of the gas turbine, we study now the ideal cycles. From the previous background of thermodynamics, we know that the ideal cycles provide the upper limit of the performance of any thermodynamic system. The performance of the real cycle, the efficiency of the real cycle is always less than the ideal cycle. We study the ideal cycles for a few reasons. The reason is that the analysis of the ideal cycle is much easier, less complicated than the real cycles. In the real cycles, there are many irreversibilities which are ignored in the ideal cycle. So for the gas turbine system, the ideal conditions which we assume are that the compression and expansion processes are adiabatic and reversible. So in the compression and expansion processes, we are ignoring any heat transfer and any increase or decrease of entropy. Similarly, there are pressure losses when the fluid flows through various components, ducts and pipes. The pressure is decreased, but for the simplicity in the ideal cycle, we ignore the pressure losses. Similarly, in the gas turbine, after the combustion process, the composition is changed. It is not simply air, and the specific heat is changed, but we ignore the changes in specific heat in the ideal cycle, and we ignore the mass flow rate changes. So we assume that the fluid is only air in the entire cycle in all the processes. The kinetic energy changes are also neglected. In the actual systems, the kinetic energy changes are there, but these changes are relatively less than the changes in temperature or pressure. So for that reason, for simplicity, we can ignore the changes in kinetic energy. Then point number 5, steady flow is assumed. The mass flow rate is constant, mass flow rate is same in all the components. In the actual case, the mass flow rate can vary because due to combustion process, due to addition of fuel, the mass flow rate can change. In the ideal cycle, we are assuming the combustion process as a simple heat exchange process. We are assuming that only the heat is transferred from fuel to the working fluid. The ideal cycle is Joule or Brayton cycle. It consists of two constant pressure processes and two constant entropy processes. For the analysis, we use the equation of first law of thermodynamics, which include the term for heat, for work, and the changes in energy of the fluid. There are 4 forms of energy considered. One is internal energy, other one is flow energy. The flow energy and internal energy combines to have enthalpy, then kinetic energy, and then potential energy. So potential energy is always ignored whether we consider actual cycle or ideal cycle. In the ideal cycle, we also ignore the kinetic energy changes. The symbol used in the gas turbine book is, the symbol for velocity in the gas turbine book is C. So we are ignoring the kinetic energy changes after ignoring the compression work is simply change in enthalpy. Enthalpy for the ideal gas can be written in terms of temperature. Similarly, Q23 is heat supplied in the combustion chamber. It is written in terms of temperature. Similarly, the work obtained in gas turbine is simply written in terms of change in temperature. The efficiency, as we know from the previous background, net work output divided by heat supplied. Turbine work subtracted by compressor work divided by the heat supplied in heat exchanger or combustion chamber. Then we can use the isentropic relation for the compression process and for the turbine process. In this formula, R is compression ratio or pressure ratio. Pressure ratio is P2 over P1 divided or equal to P3 over P4. Compressor outlet pressure divided by compressor inlet pressure is pressure ratio, or the turbine inlet pressure divided by turbine outlet pressure. Using these two formulas, we can write efficiency in terms of pressure ratio, and gamma is ratio of specific heat. So here we have to take common, we take common T4, and from here we take common T1, and then after simplification we can get this formula of efficiency. Then another important quantity is work obtained. Efficiency alone is not important. Efficiency alone is not sufficient. The work output should be sufficient. So in addition to efficiency, the work output should also be maximum. So for calculating the work output, we use the dimensionless form, W divided by Cp T1. We take T1 common, and then we can have this type of dimensionless relation. So this is specific work. T1 is the inlet temperature. For T1 we do not have any major control. We cannot vary T1 because it is the inlet temperature. Cp is related to the fluid, so we cannot control Cp. Then we have another parameter which is small t. Small t is T3 over T1. In order to have the relation in simplified form, we are using symbol T, which is equal to T3 over T1. T1 is the inlet temperature, T3 is the maximum cycle temperature. So T3 or T will depend on the maximum temperature which the highly stressed parts of turbine can stand for the required working life. So T3 will depend on the maximum temperature which the turbine material can sustain. The value of small t is about 5 to 6. So this is the typical value. This is the plot between temperature and entropy, showing the cycle under various conditions. Suppose the pressure ratio is equal to 1 or slightly greater than 1, then this will be the cycle. These will be the processes for the cycle. In this type of cycle, we will not have any work will tend to 0, because in this cycle the compression work and turbine work will be more or less same. So there will be no net work, or the net work will be negligible. Similarly, the efficiency will be negligible, because in this cycle we have a significant amount of heat supplied. You can see the temperature difference, T3 and this one is T2. So there is significant amount of heat supplied, but the work obtained is negligible. So efficiency will be also close to 0. This is another type of cycle. This is another combination of processes for the cycle. In this case also the work done will approach 0. The compression work and the turbine work are more or less same. So work done is approximately equal to 0. The efficiency can be higher in this case because there is little difference between the work, but the heat supplied is also negligible. So the numerator as well as the denominator both have small magnitude, so the efficiency can be higher in this location, but the net work will be close to 0. So this is also an undesirable type of cycle, undesirable combination of processes for the cycle. This is the optimum combination. We have work, we have to provide work from 1 to 2, and we will obtain work from 3 to 4. So the work obtained in 3 to 4 will be much higher than the work obtained when work supplied during the compression process. Since the constant pressure lines on TS diagram, they diverge with the increase in entropy. So this vertical distance is more than this vertical distance. This is the plot between efficiency and pressure ratio. As pressure ratio increases, the efficiency increases. So efficiency here will be maximum, and here the efficiency will be minimum. As the pressure ratio is increasing, the efficiency is increasing. At this location, the efficiency will be average. The specific work is 0 when the compression ratio is close to 1. Similarly, the specific work is again close to 0 when pressure ratio is very high. So you can see that the plot, the specific work is increasing, then it is decreasing. So when pressure ratio is basically P2 over P1, and P2 over P1 is T2 over T1 gamma divided by gamma minus 1. But when T2 or T3 are same, this is the condition when T2 and T3 are same. In that case, the work obtained, the net work obtained will be close to 0. This is the optimum value of pressure ratio. We can determine the optimum value of pressure ratio at which work becomes maximum. We can differentiate this relation, and after differentiation we can have the optimum value of pressure ratio at which the specific work is maximum. So we can show that this is the condition when T2 and T4 are same. When T2 and T4 are same, then the work obtained will be maximum. This is T2 and this is T4. So when T2, if the cycle is such that T2 and T4 are same, then the work obtained will be maximum. In this condition, T2, this is T2 and this is T4. So T4 is much higher than T2. In this cycle, this is T2 and this is T4. So T4 is much lower than T2. When T2 and T4 are same, then it gives the maximum work output. We can prove this relation by using pressure ratio T2 over T1, T3 over T1. So over here we put T2 over T1, and then we multiply with T3 over T4. This will remove the square sign or the square root sign. T3 over T1 is equal to T, so T cancel with T, and we show that T2 is equal to T4. So for the maximum work output, T2 and T4 will be same. When T4 is greater than T2, then we can use the heat exchanger. When we use heat exchanger, we can heat the fluid which is coming from the compressor through the turbine exhaust. But if the temperature T4 is less than T2, then we cannot use heat exchanger to increase the temperature of the fluid which is from the compressor exit. To increase the efficiency of the cycle, we can use the heat exchanger. After the fluid comes out from the compressor, and when the fluid comes out from the turbine temperature is suppose high, the exhaust gases can be increased to preheat the fluid which is coming from the compressor exit. Since there is no change in work, the work obtained will be less. So specific work is as it is. The efficiency is improved because the heat supplied is reduced. So this is the formula: turbine work subtracted by compressor work divided by heat supplied. We make an assumption that temperature after the heat exchanger of the air is same as temperature of the turbine exit. Similarly, the temperature of the gas after the heat exchanger is same as the temperature which is of the air from the compressor exit. So when T5 is equal to T4, T2 is equal to T6, we can have a simple relation for the efficiency. So this relation shows that when small t increases, small t is T3 over T1. So when small t increases, the efficiency will increase, and the pressure ratio, as the pressure ratio increases, the efficiency is decreased, because when we are increasing the pressure ratio, we are increasing the compressor exit temperature. So when the compressor exit temperature is increased, there is less chance to use the heat exchanger, because for the heat exchanger the compressor exit temperature should be lower or much lower than the turbine exit temperature. So if the compressor exit temperature is decreasing, then the efficiency will decrease and the advantage of using the heat exchanger will become less. So here we can see, with the increase of maximum turbine temperature, the efficiency is increasing. With the increase of pressure ratio for a particular value of small t, the efficiency is decreasing. This is the efficiency plot for a cycle without heat exchanger. If you are further increasing the pressure ratio, the lines can be extended, but in that case the efficiency will reduce. It will reduce below the efficiency of the cycle which is without heat exchanger, because when the pressure ratio is increased, the compressor outlet temperature is increasing, and if we apply the heat exchanger, then instead of heating, the air temperature will decrease, and when air temperature will decrease, we have to supply more heat. So in this means that using heat exchanger in such cases will decrease the efficiency, and the efficiency will be lower than the standard cycle. So as mentioned, the specific work output remains unchanged if heat exchanger is used. Then next is reheat cycle. Using the reheating process, we can increase the work output. There is a limitation with the maximum cycle temperature. The maximum cycle temperature depends on the material of the turbine. So we cannot go beyond a certain temperature value, but we can perform the reheating after the expansion process in one turbine, one section of a turbine. We can further reheat and keep the temperature or achieve the temperature same as previous, and then we further expand. So if we continue from 3 to 4 dash directly, the work obtained will be less. If we are having the process divided into two parts, 3 to 4 and then 5 to 6, the work will increase. The reason is that the constant pressure lines are diverging with the increase in entropy. So this temperature difference 4 and 4 dash will be less than the temperature difference between 5 and 6. So if we divide the expansion process into two parts, we will have more work when compared to the work obtained from a single turbine. This is the plot of efficiency. The efficiency is decreased when we are reheating. The reason is that when we are reheating, we are supplying heat, we are supplying additional heat, so the denominator is increasing. We are also achieving more work, which means numerator is increasing, but the heat supplied is relatively more in comparison to the work obtained. So for that reason, the efficiency of the reheat cycle decreases when compared to the simple cycle. Again, the temperature increase results in increase of efficiency. We can write the basic relations for efficiency. In the efficiency formula, we have the two turbine works subtracted by the compressor work, and in the denominator we have heat supplied in two portions: heat supplied during the main combustion process and then further heat supplied during the reheat process. Then using the isentropic relations between compressor and two turbine processes, we can use the isentropic relations, and we can have this type of relation for the specific work and for the efficiency. In this formula, for simplicity, this C is pressure ratio to the power gamma minus 1 divided by gamma. This is the plot between specific work output and pressure ratio. So the shape of the plot is same as for the simple cycle, but the value of the specific work will be higher than compared to the simple cycle. So reheat increases the specific work, but it decreases the efficiency. In order to increase the efficiency as well, in addition to specific work, if we want to increase the efficiency or maintain the efficiency, we can use heat exchanger along with the reheating process. So when we will use the heat exchanger, the specific work will not change, but the heat supplied, the total heat supplied will reduce. In order to save the net work, to save the net work, the other possibility is to use the intercooler. The purpose of the intercooler is to reduce the compressor work. The intercooler reduces the compressor temperature and it reduces the net work. But the intercooling process is not very common in the gas turbine systems. The reason is that the intercooling, even though slightly increases the net work by decreasing the compressor work, but the limitation is more when compared to the gain from the intercooler, because for the intercooling process we have to supply large amount of cooling water. So there is an extra component intercooler, and for the intercooler we have to provide the cooling water, for which we need a separate mechanism. So for that reason the intercooling process is not very common. Then we discuss the component losses. The previous discussion was for the ideal cases. In the real cases there are various types of losses, various types of irreversibilities. One is fluid friction, which reduces pressure, which results in pressure drop in the heat exchanger, in the ducts, in the combustion chamber. Similarly, there is some heat transfer in the compressor section as well as turbine section. So the process is not adiabatic, it is not reversible. Then for the derivation we assume that when using heat exchanger, the compressed air is not heated to turbine outlet temperature. In the derivation we assume that compressed air is heated to the turbine outlet temperature, but this is not the actual case. Then turbine work is not only used for the shaft power and compressor, it is also utilized in overcoming friction during the transmission of compressor turbine, then other components like fuel and oil pumps. Then we also assume that the specific heat is constant in turbine. In compressor the specific heat is not changing, so this is not the actual case. There is about 10% increase in the specific heat. Then mass flow rate is increased due to addition of fuel. Sometimes the air is taken from the compressor to cool the turbine blades. In addition, we have often the open cycle. In that cycle, in the actual cycle, the process 4:1 is not there, it is open. For the open cycle we use another parameter for determining the performance, which is specific fuel consumption. So specific fuel consumption is the fuel supplied divided by the work obtained. For predicting the actual performance of the cycle, we calculate the isentropic efficiency for compressor as well as for turbine. So isentropic efficiency for compressor is ideal work divided by the actual work, and the ideal work and actual work are written in terms of changes in enthalpy, and here the enthalpy is the total enthalpy, because we are also considering the velocity or kinetic energy changes. So this H will include now the flow energy, internal energy as well as kinetic energy. In the compressor, the ideal work is less, or ideal enthalpy rise is less when compared to the actual rise. So the actual work or actual enthalpy rise is in the denominator. If you are assuming the perfect gas, then we can write enthalpy changes in terms of temperature changes. So this is the compressor efficiency in terms of total or stagnation temperatures. The ideal temperature rise divided by the actual temperature rise. For the turbine, the case is opposite. Actual temperature rise is less. The actual temperature drop is less. The ideal temperature drop is more. We can write the relation in modified form by doing some manipulation, taking common TO1 and writing this temperature ratio in terms of pressure ratio. Since this is the ideal temperature at location 2, this is temperature at location 1, we can write the isentropic relation for the ideal temperature ratio. Now the actual temperature rise is in terms of pressure ratio. In the case of compressor, the inlet pressure, the inlet fluid does not have any, sometimes does not have any significant velocity or kinetic energy. So in that case we can assume PO1 simply as PA, and TO1 can be written simply as TA, because the inlet fluid does not have any significant velocity. So we can write simply PA and TA, which are the ambient pressure and temperature. When the inlet section is long, there is some pressure loss. To account for the pressure loss, we write PO1 as PA minus delta P. This is for the case of stationary plants. In the aircraft propulsion, there is some velocity of the incoming fluid. In that case, PO1 is not written as PA. Similarly, this is the relation of total temperature rise in terms of pressure ratio, PO3 over PO4. In the stationary power plants, the turbine exhaust velocity, the velocity of the fluid of the turbine exhaust is not utilized, it is wasted. So for having the proper value of the efficiency of the turbine, we write PO4 as PA. So this will give the true value of the efficiency of the turbine. For the case of the aircraft propulsion, PO4 will not be written as PA because that velocity is useful for producing thrust.